Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously, in the first part of this episode, we prepared the engine for integration with the editor, fixed a few bugs, and also added a new feature that enables the user to turn on or off renderer options. The first option that we implemented is vertical synchronization or VSync, which can now be enabled or disabled. The next step is to prepare the engine interface in order for the editor to work with it. The code for exposing engine functions to the editor is in the Engine DLL project. This code is divided between two files, where we have the functions for entities and components in the entity_api.cpp and all other engine functions in engine_api.cpp. Of course, this separation isn't mandatory, and one can choose to put everything in a single CPP file or go in the other direction and split the code into even more files. I'll start by writing a function for converting Euler angles to quaternion rotations, which can be called by functions in both files. That's why I'm writing it outside the anonymous namespace. I'm also going to add a few math utility functions for converting from degrees to radians and vice versa. Note that DirectX Math already has a function for this, which is a simple multiplication by a constant. The functions that I'll add convert three floating point values at the same time. And the constants are defined in the math types header file. Here we can call this new function where we are expecting the Euler angles to be provided in degrees. I'm also getting rid of the aligned calls and data types, since on a 64-bit platform it doesn't matter for 4D vectors, and for other vector types the cost is pretty much negligible nowadays. In the editor, we are going to use a second thread for rendering. However, our code for modifying entities and components, as well as adding and removing lights and cameras, is not thread safe. So we need a mutex to synchronize rendering and other engine operations on data. One exception is uploading and unloading resources, which is thread safe and can be done asynchronously, at least in theory. Again, I defined the mutex outside of the anonymous namespace so that it can be used by other CPP files in this project. Then we use the mutex every time we create or remove an entity. As we'll see later, we also use the mutex when rendering a frame, and that way all data access is serialized. In the last video, we added a new function that enables us to add or remove components to an already existing entity without having to completely recreate the entity and all of its components. Here we are going to expose that function to the editor. Note that the mutex is used here as well. It's pretty much the same code as create entity function, except we can't add or remove the transform component, and therefore we always pass a null pointer in the entity info. One more function that we'll need is one that returns the component ID of a specific component type. Remember that if an entity doesn't have a component of a certain type, this will just return an invalid ID. Okay, that's the minimum code we need for the entity part of the API. We can work on the engine API next. In order to be able to render anything, we need a camera, and of course we need lights so that we can see the objects that are rendered. I'll dedicate separate episodes for adding support for lights and cameras in the editor, but for now we can hardcode some default lights and a camera here as part of a temporary section that will be removed later. First, we make a new data type that will pair a render surface with a camera. I'll call it Viewport surface, since one such instance will be used for each viewport in the editor. It inherits from render surface that has a window and a graphics surface, both of which are platform independent. Here we add a new member for the camera. We also keep the geometry IDs of all objects that will be rendered in this viewport. This enables us to render scenes with different contents on each viewport in the editor. The array of surfaces is now of this type. I'll also add an array of bytes, which is just a buffer that we'll use during rendering. This is to avoid having to allocate memory every frame. We'll see how this is used a bit later in this video. Next, we write a little function that calculates threshold values. Right now, we are using the distance to camera as threshold. This works fine in most cases, but there are a few common cases where it's not great to use distance to camera. For example, when an object is large and elongated, then certain parts of it could be much closer to the camera depending on the viewing direction, since the object's center is farther away. Another example is when we use the camera to zoom in on an object by using a small field of view. This is often used to simulate looking through binoculars or the scope on a rifle. In that case, we still want to be able to view the object in full detail, even if the object is far away. A better property to use for the threshold is the size on screen where the object is rendered. We'll use screen size eventually, but for now we'll go with the simpler to calculate distance to camera for thresholds. Also note that we are using an estimated value, which is less precise but faster to calculate. Obviously, it's fine for an LOD to kick in a little bit sooner or later when the calculated distance is off by a few centimeters. Now we get to write the temporary code that I mentioned earlier, where we create lights and cameras. We already wrote that code in our test application, so we can copy and paste most of the code from there. We know that we have to create a game entity for each light or camera, so here we have a function that does that. I'm going to clean it up a little bit for our use case here. Now, when we create a camera, we first call this function to create the game entity. These are the default position and rotation values when the camera is created. We remove the entity after the camera is removed. Next, I'm going to create exactly the same lights that we are using in the test application. Well, actually, we are using a cube map ambient light right now, but before that we used 4 directional lights as our main lights in the scene. Again, we can copy that code over. Recall that before adding any lights, we need to create at least one light set that contains our lights. For now, I'll use 0 for the light set key. Finally, we set the default direction and intensity for each light and create them by calling graphics create light function. Removing the lights is again straightforward. After removing each light, we also remove the game entity to which that light belonged. At the end, we also remove the light set. Before calling these functions to create the lights and the camera for each render surface, we have to declare the mutex and the Euler angles to quaternion function, which we wrote in entity API file. We remove lights when the engine is shut down. We don't use the mutex here, because at this point we have stopped rendering. When creating a surface, we check if the lights are already created, and if not, we call create lights. Also, we use the mutex here since we are adding to the array of surfaces, which is also accessed by the render function, as we'll see shortly. And instead of creating a render surface, we use a viewport surface, which includes a camera. Removing a viewport surface is easily done by removing the camera, graphics surface, and finally the window. Again, we use the mutex to lock access to our data. This mutex needs to be used everywhere we access the array of surfaces. Let me close this file and rebuild the project to hopefully make Visual Studio come to its senses. When resizing a viewport, it's important to adjust the aspect ratio of the camera accordingly. Now let's add a function that will fill in the array of geometry IDs to be rendered in each viewport. This array of IDs will be passed from the editor to this function. We can simply copy the content of the array using a memcopy. Note that passing an empty array is the same as having an empty scene. Finally, we write the render frame function, which uses the geometry IDs for the given surface to render the scene. Again, here we use the mutex to lock access to our data. Then we use the frame info buffer as a block of memory that contains render item IDs, threshold values, and entity IDs. We calculate the offset for each array within this buffer and assign the pointers accordingly. Then, if there are any items to render, we get their render item IDs and calculate their threshold values, which also fills in the entity IDs. At this point, we have all the information that we need in order to fill in the frame info and call surface render function. Note that for now we use a default light set and camera. This should be create light. Now the code compiles, but we get this linker error about an unresolved external, which, to be honest, I have no idea why it's happening. So let's investigate. It's telling me that this function is not found within the object code. This is a function from the engine library, so let's make sure the library file is specified. Okay, that didn't help. Well, the function is right here and is part of the engine library, so I'm not sure why it can't be found. I have really no idea what's going on with this. I'm looking around to try and figure it out. I won't change any code or project settings, so feel free to skip to this timestamp for the solution. At least I'm assuming that I'll be able to fix it somehow. I'll delete the .vs folder and restart Visual Studio just to be sure that it's not confused again. We are also already specifying engine.lib in the DLL main, so we don't have to do it here again. Speaking of DLL, let's check if we are not missing anything configuration-wise. Let's look at linker options for Engine DLL. Note that it's using the debug editor build config. What's catching my eye is that we don't have the use with editor compiler definition here. I always assumed that Engine DLL project wouldn't need it since it's always used with the editor, but somehow it might have an effect on how it's linked with the engine, which does need this compiler definition in order to work with the editor. So let's add it and see if that helps. We'll add it for both debug editor and release editor build configs. And that was apparently the cause of the problem, which is now fixed. Okay, awesome. Let's start the editor to see if it works. So the other day I made the mistake of installing a new version of Visual Studio to see what they had improved this time, and now it's somehow not letting me open an instance of Visual Studio 2022 using its process ID anymore. Now I have to temporarily change this, which opens the new version instead. I'll set it back before committing the code. The editor appears to be working fine. We get this assertion failure when closing the editor, which tells us that not all resources have been released. Looking at where it happens, we see that it's in a descriptor heap, and the heap type is render target view. Remember that we added graphics surface creation today, which creates the swap chains and the render target views. Now, although we do try to remove the swap chains in this function, you can see that it's never called. This is because we are calling it here in destroy window core function, which is in this case not the right place to do that. We'll see in the next episode how this issue is fixed. So as you might have guessed, we are going to work on the editor side in the next episode, and with that we have come to the end of this video. Thank you as always for joining me, and I'll see you next time.